circuit board power on. The surrounding components remain at baseline temperature, but this single component immediately radiates an intense, glowing orange heat signature. Standard textbook schematics often represent this component as a passive mathematical constant, a simple R in an equation used to calculate current. Functionally, a resistor is a highly deliberate energy conversion device. It is engineered to alter the physical state of the electrical system it inhabits. To understand how a circuit actually behaves, we must look past the ideal models and examine the microscopic atomic mechanics driving the component. Treating resistors as theoretical ideals rather than physical energy converters leads to catastrophic hardware failure in advanced engineering. We begin by moving past the exterior casing of the component and down into the internal crystalline atomic lattice of the conductive material. When an external electric field is applied, the free electrons in the material move in a uniform direction. This localized acceleration is known as drift velocity. This 3D model of an atomic lattice visualizes the mechanism of resistance. As the free electrons accelerate through the structure, they repeatedly collide with the much larger, relatively stationary lattice ions, continuously losing momentum and altering their trajectories. These are inelastic collisions. The kinetic energy lost by the accelerating electrons is absorbed by the lattice structure, manifesting as vibrational energy, or phonons, causing the ions to oscillate rapidly. This microscopic increase in lattice vibration translates directly to a macroscopic increase in temperature. The component generates heat. Resistance is this inescapable thermodynamic process of energy dissipation. A resistor restricts flow by converting electrical kinetic energy into thermal energy. We can now pull back from the atomic scale to examine the macroscopic effect this conversion has on the entire circuit board. This 3D elevation map illustrates the continuous electrical pressure, the voltage topology, running across a series circuit branch. The flat plateau represents high potential energy moving toward our component. As the charge enters the physical span of the resistor, the localized energy dissipation causes the voltage to drop sharply, stabilizing at a strictly lower elevation on the far side. This predictable drop in potential energy dictates the pace of the system, limiting the rate of charge flow, the current, through the remainder of the branch. While heat generation is the intended function of the component, unmanaged thermal load destroys the physical material. If the temperature climbs too high, it triggers thermal drift. The excess heat alters the intrinsic electrical properties of the conductive material, shifting the internal resistance value away from its intended specification. Resistor design is a constant physical battle to stabilize intentional energy conversion while preventing the material from degrading. Early circuit designs managed this thermal threat with a brute force solution, the carbon composition resistor. This photorealistic CAD cutaway reveals its internal architecture. It consists of a solid, macroscopic volume of carbon powder bound together with a ceramic filler. By utilizing a dense, bulk mass of material, the component achieves massive thermal capacity, allowing it to absorb high-energy, sudden transient voltage spikes. The internal structure of the carbon and ceramic mixture is entirely random. Because the particulate mix is unengineered, electrons navigate an unpredictable, jagged path through the material. This chaotic flow generates significant electrical noise and high margins of error in the component's true resistance value. The bulk structure sacrifices signal precision for raw survivability against power surges. Modern circuitry requires tighter tolerances than bulk carbon can provide. The engineered response to this need is the metal film resistor. Looking at this CAD cross-section, the architecture is distinct. A solid ceramic center is wrapped in an incredibly thin, highly uniform layer of metal oxide. The accuracy of the component comes from a laser-cut helical spiral carved directly into that metal layer. By etching this spiral into the film, the physical path the current must travel is lengthened and strictly controlled. Manufacturers dictate the exact final resistance value with high accuracy by making micro-adjustments to the pitch and depth of that spiral geometry. This continuous, engineered path eliminates the erratic electron flow seen in carbon components, removing the resultant signal noise. In modern analog circuitry, engineered geometric boundaries define tight tolerance performance. When an environment demands sustained extreme heat dissipation, thin metal films will fail. The architectural solution scales up to the wire-wound resistor. This cross-section shows the structural shift. Microscopic films are replaced by a heavy-gauge conductive wire wrapped tightly around a structural core. The large physical mass and heavy wire gauge provide unmatched surface area, allowing the component to continuously shed extreme heat into the environment. Cautionary: both wire-wound and metal film architectures rely on a helical, coiled shape. Coiling conductive material introduces a secondary physical effect. This schematic visualizes parasitic inductance. Passing current through any coiled structure generates an unwanted electromagnetic field. These lines bloom outward from the loops and actively resist the flow of the current itself. When subjected to high-frequency signals, like radio frequency transmissions, this parasitic magnetic field causes the resistor to behave unpredictably. The high-frequency wave is violently choked off and distorted by the expanding field. Maximizing a component for extreme thermal power or high physical precision introduces secondary traits that restrict its use in other applications. These two operational environments require strictly opposed component architectures. On the left, a heavy industrial power supply; on the right, a high-frequency radio transmitter. The heavy wire-wound resistor is assigned to the industrial power supply. Its massive thermal capacity is the trait that guarantees survival under that sustained load. The RF transmitter requires the metal film resistor. Its geometric stability and lack of parasitic magnetic interference ensure the high-frequency signal remains intact. The physics of electron scattering and heat generation are universal. The material architecture required to manage that heat is hyper-specialized. Rigorous electronic design relies on specific material solutions engineered to overcome exact thermodynamic and electromagnetic constraints.